today we continue topic about interfaces. Well, actually, today we have two lectures about hardware. But because it's day before your holidays, I think that we skip the quiz today. Because some of you are a little bit stressed about it. Okay, so this is initial info for you. Okay, so now I'd like to tell you something about the most commonly used computer interfaces. Yesterday I told you about the fastest interface on mainboard, so which is the memory bus. Now I'd like to tell you about interfaces which are used to connect peripherals, so extension cards like graphic cards or hard drives and other devices. I'd like you to understand what happened or what are the trends and what's changes in computer and interface architecture in last let's say 10 years. So I start from the obsolete interface to show you how it evaluated from PCI to, let's say, PCI Express. So PCI was very popular interface. Now it is presented on server mainboards or in better mainboards, but most devices are connected without PCI now. So look, on mainboards there were slots, very characteristic slots, which looks like here. And this interface, it was a bus interface. So there was short pool of lines, and they were shared among devices which could be connected to the slots. What else? If there were more devices than we have slots, we could add extension or passive extension card. So this card was inserted in one of the slots, and we could easily extend the number of slots. So we were able to connect up to, I don't remember exactly, but 100 or 200 of devices. Okay, so the bus consisted of 32 or 64 data lines. There were also additional lines. The clock frequency was 33 or 64 megahertz, depending on version. And throughput was up to 500 megabytes per second. So it's not so huge, but it's higher than, let's say, USB 2. There were different versions of PCI, like AGP, which was used to connect graphic cards. But in fact, the PCI was the first technology which supported something which was called plug and play. But sometimes we can say plug and pray, function. So this function led to attach device without prior configuration. So device which was attached to PCI bus was configured automatically. So the address was given, some registers were set up. Before this era, there was a bus which was called ISA, and this device, every device which was connected to this bus could be pre-configured using physical switches. It is not important to remember, but you should understand that PCI consisted of parallel bus. There was also a clock signal, so it was a synchronous line reset, which was used to reset device, and 32 or 64 lines, which were used to send data and to send address of device. There were interrupts. So the mode in which device on PCI were handled used interrupts, not polling. But we have only 4 interrupts, so they were shared among the device. If we have more than 4 devices, the special groups were created. So as I showed you before. We could think that PCI Express, which is the most commonly used interface now, okay, interface to connect, let's say, fast peripherals, is the child of PCI, but in fact PCI Express and PCI differs very significantly. So it is hard to tell that PCI Express is, you know, the evaluation of PCI. So the difference is that PCI Express is a serial point-to-point interface. It's not a bus interface. So if it is a point-to-point interface, it lets us to connect only a single device to particular, you know, slot. So with the number of devices we are able to connect is limited, and it depends on chipset parameters or processor parameters, and we can't extend it. In case of PCI, okay, we could easily add a slot extension, and we were able to connect more devices if we need. The interface or the subsystem which is called which is used to communicate between 2 devices using PCI Express is called lane. So lane consists of 2 pairs of differential wires for each direction. So in fact we have 4 wires which are used to communicate in full duplex mode. Every device is connected to controller, so 2 devices are not connected directly, but every device is connected to controller. The controller is embedded into processor or in chipset. but mostly most processors supports this function. This signal is transmitted using voltage signaling or differential voltage signaling. So it's low level voltage, less than 3.3 volts, and it used block coding. So you can see that the channel coding is 8B over 10B, or for PCI Express 3, and for it is 108B over 130B. So it led us to achieve the bit coding redundancy, so we can ensure self-synchronization every, let's say, 3 or even 2 bits. So using this coding, we are able to stream data with very high speed. Yeah. So look, in PCI Express, the throughput of interface is 16 gigabits. So it's 2 gigabytes per second brute. Yeah. So with an additional elements which are used to send data. But probably most of you have laptops, so you don't know how the main board in desktop computers looks like. Of course, in laptops there is also PCI Express interface, but okay, it looks a little bit different. But on main boards, you can find PCI Express in different versions. So you can see that here we have 5 slots, and the top 4 slots are PCI Express slots, and this bottom slot is PCI slot. So what is the difference? So why there is so many different slots? In PCI we have only a single type of slot. Here we have at least 3 types. So the difference relies on number of lanes which are connected to slot. So here we have 8 or 16 lanes attached. Here we have 4 lanes attached. Here we have up to 2 lanes attached. So so this it makes difference, but you should know that the lanes are multiplexed. So if your processor or chipset is able to handle, let's say, 16 lanes, and if you sum up all lanes or all slots you have on your main board, you can get the higher number of lanes from this calculation. So let's say here we have 16, so 32, 34, 38 lanes. Yeah, but your processor is able to handle only 16 of them. So what happened? If you connect here 2 graphic cards, there is a risk that it doesn't work, because okay, lane is point-to-point interface, so it is impossible to connect more devices than the number of lanes is. Of course, you can decrease the speed of particular device, so some devices may use 16 or 8 or 4 lanes. The result is that it works slower, but it still works. But if you want to achieve the highest performance, you should to check whether your processor supports the number of lanes you want or you need to use. Okay. So there is a risk that if you connect two peripherals to this wider slots, you would be not able to connect other devices to this shorter slots. Okay. Okay. So that was the PCI Express. In case of laptops, we don't have the slots like this, but we have PCI Express, which is used, for example, to connect hard drives or solid state drives. And what is the name of this interface which utilize PCI Express? And M2 is the format of socket which is able to connect a solid state drive, but M2 may handle both serial ATA and something which is called NVMe. So NVMe is the name of PCI Express for laptops, which is used to connect hard drives. Yeah. So yeah. So remember that if you have solid state drive and there is written M2, it doesn't mean that this hard drive supports PCI Express. So M2 format. Okay. So look. So here, I think now is the most commonly used format for hard drives in laptops. But if you try to buy M2 interface, you have to verify whether is NVMe, yeah, or serial ATA. Because M2, so you can, if you try to buy hard drive, you can see that for M2 you have the cheaper hard drives use serial ATA, and the more expensive they use NVMe. So both of them has M2. But remember that whether we are able to connect NVMe or serial ATA hard drive, it depends on the main board. Yeah? So we can't connect any of this too. So if your main board or slot supports NVMe, okay, you should connect NVMe. If not, probably you should connect serial ATA. Okay, the next interface, which is used to connect hard drives. The older version of this interface is called P.ATA, so parallel ATA, advanced technology attachment. So let's say 20 years ago, it was really advanced technology, but now it is deprecated. So it is not enough to stream data with speed that or throughput which can be used. Okay, so look, the connector, so this is the bus interface. So we were to single slot, we were able to connect up to 2 devices. So it was bus and the throughput was shared among two devices. The throughput was 133 megabytes per second, so it was, you know, enough for hard drives. Now hard drives are even faster, but okay, it was okay. But when the serial ATA or solid state drives were introduced, it was, you know, too little. So this interface was substituted by serial ATA. So in case of PCI Express, it's not, you know, PCI Express is not able to totally substitute PCI because the limitation of in number of devices. In case of serial ATA, yeah, it was the progress which was made. So this interface, ATA interface, was substituted by serial ATA. So what happened? Here we have parallel and here we have serial. So this interface consists of 7 wires. So we have two lanes or 2 pairs. So we have 4 wires for full duplex transmission in differential low voltage mode. And we have 4 ground lines. So look, here we have a connector on the side of hard drive. And what is the typical, and you can observe that there are paths of different length. So we have longer path to shorter paths, longer path to shorter paths, and longer paths. So what do you think? Why it is so? Why we have so different paths length, and are you able to tell me which signals are connected to which of these paths? Does anybody know? Okay, so look, we have 2 differential pairs. So this shorter path refers to TX and RX because we have differential mode. To send signal, we have two wires, so we have to have 2 paths. These longer paths are ground paths. So there are several issues. First, you can see that the ground paths somehow surround the transmission lines. So I have ground, transmission lane, ground, transmission lane, ground. So this ground lanes creates a shield. So it separates 2 transmission lanes. So it protects against crosstalks. Okay, so it's the first issue. So therefore we have so many grounds here. The second issue is why the ground paths are longer. this is very typical for technology which is called a hot swap. So hot swap technology lets us to connect device when it is powered on. Otherwise, we should turn power off the device and then we should connect, or we can connect it. So first, when we connect device, it is mechanically, mechanical feature. So first, when I connect the hard drive, the ground lines are connected. So it makes the potential of both devices equal. And then after, several milli or microseconds, then the signal lines are connected. If it would be done different, or the length of these paths were equal, it may happen that a high voltage would be generated on signal lines. So in this case, the receiver or transmitter could be broken. So it protects against something which is called ESD, so electrostatic discharge. Yeah. Here we have connector which is used to supply the device. And you could see that here also we have different paths length. So again, the longer paths belongs to ground and the shorter paths belongs to voltage. So using this method, we are able to, make the reference voltage equal. Okay, here you could see the throughput for particular version of serial ATA. So it let us to stream up to 600 megabytes per second. In case of PCI Express, it was 16 gigabits brutto. Okay, it's about 2 or a little bit less gigabytes per second. So look, if we compare serial ATA with parallel ATA, it seems that this technology was more expensive because, okay, we even for the cable, we need more lines, bigger plug, and so on. Here we have only 7 lines. And even we have less lines, the interface is cheaper. The throughput is significantly higher. So look, sometimes we think that technology has to be to gain a better performance and so on. The technology has to be much more complex, so the devices should be bigger. And here you could see something opposite. Huh? We have simpler solution, which works better. Of course, it was achieved by using channel coding, so we are able to transfer serial data on very high speed and ensure self-synchronization. So it was the clue thing which was a breakthrough to start developing very fast serial interfaces. Up to this time, the parallel interfaces were the most prominent. Okay, another interface, which is, you know, a serial, let's say, a parallel interface, parallel connection of serial interfaces. It is called HDMI. So probably you know it. It is used to connect your displays and other multimedia devices. This digital interface, so the data is sent in binary mode. Looking at Planck, you could see that we have 3 lanes. So we have 3 data streams we are able to use in both directions. So we are able to send data to device, and we are able to receive data in opposite direction. What else? We have clock. So this interface is synchronous interface. It is typical because in case of displays, we have to ensure the synchronization between, you know, the value and the position of a particular pixel. So this clock device is used to for this purpose. We have also different interfaces here. For example, E2C interface, which is used for low speed communication between the device and computer. Looking at the throughput is about 6 gigabits netto. It seems to be less than in case of, let's say, Serial, ATA, or PCI Express, but opposite to these interfaces, HDMI can have longer links. So you can have, let's say, 10 or even more meters of the cable, and you are able to connect your device with this speed. It is impossible in case of, you know, Serial ATA or PCI Express. Now I'd like to tell you something about USB, which seems to be most commonly used interface for, you know, external devices. There was a huge progress which was done in this technology, so we should be conscious that the USB 2 and USB 3 are, you know, almost totally different technologies, even the name is the same. So let's start from the appearance of USB. So probably you know that there are different plugs and different connectors which are used. So in fact, in USB, because this is a bus interface, so we have a shared links. So this link is shared among different devices which are connected. We have every cable has 2 different plugs. So we have something which is called A and B. A is connected to device which is called host. So host is the device which governs or is a master for this bus. B is connected to device which is called, you know, device or slave. But if we have, for example, micro USB or okay, USB-C is not in fact USB interface because it's only connector for different for many purposes. But if we have the mini or micro USB connectors, they are AB, so they can be connected both to host and device. How it is, detected, I will tell you later. So for this type of plugs, the interface consists of 4 lines. So we have ground, power supply, so 5 volts, and we have two lines, differential line. So they are denoted as D plus and D minus. And look on this plug, you could see that they're similar to serial ATA. The data lines or paths are shorter than ground and power supply lines. So it is first if you connect your device first, the ground and voltage are in contact, and after some time the data lines are connected. So it led us to connect USB when your computer is turned on. But if we have two differential lanes, so single pair or single lane, it means that this interface is half duplex interface. So in particular period of time, only a single node can send data. So it's not full duplex. In case of USB 3, you could see that this plug, which is similar to USB plug, has 5 additional lines. They are, they are not visible, but dependent on, you can use this plug to connect both to USB 2 connector and to USB socket. Yeah. So if you connect USB to USB 3, these deeper paths are in contact. And now, if they are in contact, you could see that there are 2 lanes. So I have separate lane for receive and separate lane for transmit data. So in case USB 3, we have not half duplex, but full duplex mode. The question of Mr. Korzeniowski was how it is. I don't understand this word, wyrd, because
in Polish it's dziwak. It's talking about
wire. Okay. Okay, I don't know the answer why. In fact, I don't understand your idea or your question. There are, I think that in electrical sense, the micro and mini USB, there are no difference in micro and mini USB. Compared to AB, plugs, there is a difference because there is an additional line. So I have not 4, but I have 5 lines in this connectors, but there are no electrical difference. So what is the reason that they are called? I think micro is smaller than mini, yeah. So maybe it's the reason that that it was called like that. You asked about second from left. So this one, yeah, this one is not typical. It's not micro or mini USB, but it is also used for I think for cameras and other devices. But now I'd like to tell you about ID line. Okay, Mr. Nikitin, I will tell about USB 3 and 3.1 later on. I hope that I have slide about it. But now I'd like to tell you something about ID line. Look, if you have your mobile phone, it may operate on 2 different modes because you can potentially connect keyboard or pen drive. And in this case, my mobile phone or tablet behaves like master. So it governs the bus. So other devices are slave. But if you connect it to your computer, it behaves like slave. So the master device is your computer. This mode is called on-the-go mode. So the on-the-go device can be master or slave depending on the situation. And ID line is responsible or is used by on-the-go devices to detect whether it should be master or slave. So if you have a connector like this, and we have the cable which is micro USB on the both sides, or we have device which has like pen drive with micro USB plug, the ID lines can be connected to ground, or it can be disconnected. So in this case, on-the-go device recognize whether it should be host or device. Okay, so you should know that this line exists and what is the purpose. Okay, so what is the difference between USB? Okay, I don't have the value for USB 3.1, but the difference, the most visible difference between them relies on the throughput. So in USB 3.2.0, it's about 480 megabits per second, while for USB 3.0, it's 10 times more. In case of USB 3.1, there is a difference in speed, but there is also a difference in power supply. So in 3.1, we can charge or we can source higher current from the interface compared to USB 3 or 2. So look, for up to USB 2, the line coding was not a block coding like for faster interfaces, but it was simple voltage coding which utilize NRZI. Yeah, so no non-return to zero inverted. So it was the method which was used, but the throughput of this interface was limited because we were not able to, you know, to clock this interface with higher speed. As I told you, in USB there are two different nodes. So there is a host node, so there can be only a single host, and device node, and we can have up to 127 devices connected. We can have also a hub node. So the hub is a kind of splitter, so it lets us to split the bus on different devices. So we have a port. Yeah, there are also on-the-go devices. So device which can be host or device depending on this on situation. USB has three technologies topologies. So we have controller. I don't have tablet now, but okay. So here we have host. Maybe it's not good visible. So here we have host, and host is connected with hub. So usually the hub so hub is kind of splitter. So in your notebooks, you have, for example, several USB ports, but depending on your notebook, there is one or two controllers connected. Yeah? So, so for example, if you when something is wrong with your computer, for example, your keyboard is broken or touchpad is broken or camera doesn't work, you should know that every of these devices are connected via USB. Yeah? And you call to support, and first, which you you are asked to do is, okay, so please take the plug USB connector on your left side of computer and connect mouse, for example, and please verify whether it works or not. So if, for example, something is broken, so this led to examine where is the problem. So let's say if we have a single host, so single USB controller, and the serviceman knows that to this controller there is a hub, and to this controller is the keyboard is connected, and a single external port is connected. So if keyboard doesn't work and you connect mouse or other device to particular port and it doesn't work, it means that something was wrong with hub. So it tells you to send your device back. But if the mouse works, it means that something is with your keyboard. So probably mechanical problem, or yeah. So this is quite simple way of how we can diagnose, make diagnosis what's going on. So if we have two controllers on your computer, so we have usually two hubs, and you can find that, or if you know, it's good for you. So if we have many many USB sockets in your computer, and we know that this socket belongs to particular controller, and this socket belongs to different controller, and we want to, for example, connect high-speed device like external hard drive. So if you connect it to controller where keyboard, camera, and other devices are connected, the performance will be lower than performance when you connect it to controller where nothing is connected. Because you should remember that this is bus. So the throughput of this interface has to be shared among all devices which are connected. This interface has three topologies. So, for example, we can have additional hub here. And this hub is able to split signal on different, on other devices. Yeah? And we have to, so we can have up to 7 levels. So we can have up to 7 hubs. But you should know that, for example, if we have external camera, it is recorded or it is recognized as composite device. So this device has hub embedded, and in fact it consists of 2 devices: video device and audio device, so microphone device. Yeah? So in this case, we have additional level of this topology and 2 separate devices are detected. Okay. Having USB device, every device which is connected to USB has to be classified to one of these classes. So it can be recognized as audio device, as communication device, as human interface device, physical image printer, mass storage device, USB hub, smart card, and so on. Yeah? So it doesn't matter what the device is, it has to be recognized as one of these devices. Why? Because depending on the device type, there is a different polling policy for this device. So I told you about polling here. So because in USB we have only 4 lines, there are no interrupt lines. Every device has to be polled by master. And depending on the device class, there are different polling policy which is applied. For example, if we have human interface device to this class, we can, so every keyboard, every pointing device like mouse, touchpad, and so on, is recognized as human interface device. What is the typical for this class? The typical is that this device is polled very often. So depending on USB version, is about 1 kilohertz, so every 1 millisecond or every 10 milliseconds. Okay, so great. We have, device of very high responsiveness, but there is a certain limitation. This device in a single package can send only 65 bytes or 64 bytes of data. So in fact, if we want to use this device to stream data, it is able to send 65 kilobytes per second. Okay. So this device can't be used to, stream data in real time. But we can achieve high responsiveness. Okay, so what's about audio device? So in audio device, the throughput has to be significantly higher, because if we stream data with 45 kilohertz sampling frequency and with 60 or 24 bits, 16 or 24 bits, we need higher throughput. But what is the problem? In this case, the protocol assumes that some packets can be discarded. So if something was wrong or USB was, too busy, the packets are discarded. So average throughput is guaranteed, but the data consistency not. So, okay, we can use this device to stream data, because if you stream data and something will be lost, let's say two packets, it's even hard to hear it. Okay, oh, you can hear a small lag or something like that, but we have a real-time stream, and this is the most important thing. Okay, on the opposite side, we have mass storage device. So if device is classified as mass storage device, the transfer time is not guaranteed. So there is not guarantee that this device will be handled every 1 millisecond, but this device can stream data or many data, but and the data consistency is guaranteed. So we know that everything which was sent will be received, but the time is not it's unknown. So it is possible that there will be a huge lag in transfer. Okay, so you can see that there are no perfect class. So the class which led us to stream a huge amount of data with high performance, and which led us to obtain high responsiveness and data consistency. Yeah, so there are no such class, because if in this case this class would so should possess all bus. And here the assumption is that we have different devices and we have to share this bus among these devices. So it is impossible to have device which takes all. Yeah. Okay, I think that it's not so important for us. Here you have a list of transfer types. So depending on device class, different transfer type is assigned. So we have synchronous transfer. So so it is used for audio video. So transmission speed is guaranteed, but some data can be lost. Interrupt transfer. So it is used for human for human interface device, and in this case we are able to obtain high responsiveness. And bulk transfer for mass storage devices. So it let us to stream data, so huge amount of data, but the time is not guaranteed. Okay. And we have also something which is called control transfers. So in this case, the control transfers are used for, communication between controller and the node to set some parameters. Yes, I will upload it. Do hubs control only one type of plug? Mr. Welsh, I think it is possible to have the hub with different sockets, but frankly, I haven't seen such hub. But in theory, of course, it is possible. Okay, now I'd like to tell you something about USB-C. So first, it is called USB-C, but in fact, it's not USB. So USB-C is only a name for connector, not a name for interface. Why? Because if you look at the USB-C connector, you could see that there is a lot of different lines which can be attached. So in fact, USB-C intend to be a substitute for all connectors. So like a Swiss Army knife. Good comparison. So inside this connector, we can have a USB 1 or 2, USB 3 interfaces, audio out interface or microphone interface, display port, HDMI, Thunderbolt, MHL, and supply. So it is the intention is to have a universal connector which let us to connect everything. Yeah? So this is the most important difference between USB-C and the connectors I showed you before. Of course, if we have USB-C socket in your computer, it doesn't mean that everything is accessible. Yeah? Because it depends on the computer architecture, what is connected to particular path. But now I'd like to tell you about something about the most important feature, and I think USB-C is kind of somehow, or maybe somehow, a breakthrough technology. Of course, if every notebook or laptop or computer will have this connector, it may be. Of course, you probably know how iPhone was cope with USB-C requirements, because EU requested that all devices should have USB-C let's say connector. So most manufacturers use USB slot in mobile phones or tablets, but Apple doesn't. So, but they provide a cable with USB plug. So it's the solution how they cope with this rule. But what is very important? The most important thing that if we use USB C, we are able to source up to 100 watts of power. So you are able to power every notebook, every device. In case of USB, we were able to source up to 500 milliamps of current. So it's about 10 watts. Here we have 100 watts, so 5 amps. Regarding the size of this plug, it's very really it's very impressive. What else? If you look at this interface, you could see that on the top side and the bottom side, we have elements which are, you know, mirrored. So here I have GND, here I have ground. 2 lines of TXT, 2 lines of TXT, VBus, VBus. So so you can see that every path is doubled, but okay, they can be connected to different devices. But what is the benefit of it? The benefit is that I can connect USB-C in any, maybe not in any orientation, but there are no polarization. So I can connect this plug on using one on the one side, and I can turn it by 180 degrees and connect it also. In case of USB 2 or USB 1 plug, sometimes, okay, this is my experience, maybe you're not, but sometimes I have to try even 3 times to connect it properly. Yeah, so so it works good. The second or the third benefit is that it's very so you can perform up to 100,000. I don't remember the right value, but about 100,000 times. So it's very mechanical resistant, or it should be mechanical resistant. Okay. So now, in theory, if you have a single USB-C connector and you can connect your laptop to, you know, at the same time to your display, to supply this laptop to your network and so on. So it's really useful. Okay. Now I'd like to tell you the last slide of this lecture is about Thunderbolt. So look, here USB-C can have something which is called Thunderbolt interface. Yeah. So now I'd like to tell you several things about Thunderbolt interface. So in fact, Thunderbolt interface is the version of PCI Express which can be which has form of external interface. So far, PCI Express, which is one of the most of the fastest interfaces, was limited to devices which are embedded. Huh? But Thunderbolt let us to expose it outside. So using Thunderbolt, we are able to connect, for example, external graphic cards or external high-speed devices or 8K display. So we are able to stream data up to 30 gigabits per second. Yeah. So it's really impressive speed. So in fact, using Thunderbolt, we can have, external dock station, which has many peripherals or high-speed peripherals attached. You should know that Thunderbolt is PCI Express, so every device which is or simulate or is compatible with Thunderbolt can create many different interfaces like DisplayPort or HDMI and others. So here we have very high speed interface, and the Thunderbolt controller is able to expose other interfaces which are needed. Okay, so I think that's all for about interfaces. So I will try to download it or upload it on YouTube. So now I'd like to start the lecture, which is somehow a continuation of the lecture about interfaces, but I'd like to focus on computer networks. Okay. So what's okay? So the computer network is, of course, a kind of interface or many interfaces. But I think because the networks are so popular, there are a lot of security issues. I think that it is good to know something about how network works and what are the problems and risks. Okay, if we have a computer network like this, then we can have different topologies. So the most commonly used topology now is topology which is called a tree or star-like topology. So we have computers which are connected to a single box which is called a hub or switch. But we can stack switches, so we can connect switches in tree-like structure. But in fact, you should know that looking at the way how data are transmitted, this technology or this topology has some features of bus. So, for example, it is impossible that two computers can communicate in any time. So it's not a full duplex connection, yeah? Because some elements of this architecture are shared among different devices. So in this case, there has to be a kind of collision, detection procedure, which decides who can send data in a particular period of time. So here you have a basic topologies. So we have star or tree-like topology. We have bus topology. So in this topology, the devices are not connected to hub or switch, but they are connected to single lane. We have ring topology. So looking at the ring topology, this topology is more robust for interface failures, because if the link is broken in any segment, it creates a bus or star topology. So look, the computers can communicate with each other independent on the failure of one of the segments. Okay. But if we have wireless interface, what do you think? What is the topology for wireless interface? Are we able to classify a star? Of course. So we have access point, and every computer connects to access point. When we so presenting or talking about when we talk about the network, it's good to divide the aspects which are related to network into layers. Yeah. So here you have a model ISO-OC. This model is used to describe different aspects of network, and also to make the network technology more flexible. So we have 7 layers here. So we have physical layer, data link layer, network layer, transport layer, and so on. And for every layer, different aspects are considered. So for example, for physical layer, the most important aspect is what is the way how particular bit is coded. So depending whether we have optic fiber or wire or wireless, depending on the medium type, the bit will be, coded in different way, using voltage, using light signal, or other way. So, but if we go to upper layer, data link layer, for us it is not important how particular bit is coded, because it is done on the bottom layer. So now we want to send a stream of bits. So physical layer cope with the coding bit into particular type of signal, but on this layer it is important how to send the data from one node to neighboring node, and so on. If we go upper to network layer, for us it's not important how to send data between 2 neighboring nodes, because it is done in frame layer. But for us, it's how to send data from one segment of network to another segment of network. So you can see that going up, every layer is much more abstract. So for network layer, for example, it is not important whether we use optic fiber or we use a wire or wireless technology, because it's, you know, homogeneous from this perspective. Okay, so let's go to the let's look deeper in particular layers here. So let's start from the physical layer. I told you that this layer defines line coding method. So everything I told you about the block coding or line coding is implemented in physical layer. So how particular bit or set of bits is presented. So in this layer, if we have transmitter and receiver, the transmitter should be able to detect a string or stream of data which were sent to receiver, or it should be able to detect whether the stream of data is corrupted or not. So in physical layer, we have to define pins or type of connector, voltage levels, etc. So when we go up, so data link layer, it led us to connect node, so to perform node-to-node transfer. So we want to transfer data between two directly connected nodes. So for us, it's now not, okay, it's important to send particular bit or set of bits, but we want to send something which is called a package. But what else? If my device is connected to several nodes, I have to be able, I need to be able to, you know, select the proper node I want to send data. And in data link layer, every node has a unique address, which is called media access control, so MAC address. So this address led me to identify the particular node to which I'd like to send data and to send data there. So now, not only a group of bits is sent, but the full package will be transmitted. Yeah. Okay. Several words about MAC address. With, I like to show you something, but I need to turn the recording off because I don't want to make my MAC addresses public. But look, every device which is connected to computer network has media access control address. So this is the most important address which let the devices to recognize them in the network. Of course, most of you know that there is something which is called IP address, but I will be talking about this address later. So what is the MAC address? The MAC address consists of 48 bits. So it consists of 6 bytes, and first 3 bytes are used to recognize the manufacturer of particular interface like network card, and other 24 bits are the unique identifier for this network. We can assume that in particular network, all devices which are connected has a unique IP or MAC address, not IP, MAC address. It should have. If not, okay, there is certain problem. Okay, I will tell you something about package routing using MAC address later, but now I'd like to tell you something about collision detection, because collision in a data link layer, the collision detection method is applied. So I told you about collision avoidance method. Now I'd like to tell you how collision detection works. So in computer networks, when we have many devices which are short particular network, in this network only a single device can send data at the same time. So how it is done? If particular node starts to send data, it verifies whether data which were sent to bus are the same like data which are read from bus. So the process is the same like for collision avoidance. But the reaction is different. So first device verify whether the medium is idle, so there are nothing is sent, and it starts to send data. Okay, the problem is that because every node has to wait until the medium is idle, but if we have network and there is a distance between two nodes in this network, the signal propagation latency may be about several milliseconds. So if we have network of size 100 meters, it may happen quite often. So in this case, even the medium is in idle state, it may happen that two nodes will start sending data at the same time. So in this case, if particular node detects the collision, it sends something which is called a jamming signal. So jamming signal is the signal which disturbs everything, like a stream of high and low state on the bus. And in this case, every node is able to hear it. So even this node which which sent data at the same time and couldn't detect the collision. So after transmitting the jamming signal, every node wait for a random amount of time. This time is not totally random because it depends on the MAC address value. So we can expect that after this time, there will be no collision because every node will retry transmission in different period of time. So the first who start transmit data should win this competition, because if it starts transmit data, other devices have to wait until the medium will be idle. But after 16 consecutive attempts, so if the particular device tried to send the data 16 times and every time there was collision, this device stops transmission. So it's disconnect from the network, silent. Okay, so here you can see that in data link layer, we have different methods. So we have addressing and we have collision detection implemented. Then we go up to network protocol. Oh, sorry, it's time for break. So yeah, so we have 30 minutes of break. So thank you for attention, and we will see in a moment.